So specifically, X-ray photoelectron spectroscopy, or more commonly known as XPS, will ionize core electrons. All right. So here you can see is our Bohr model diagram of an oxygen atom with its various electron subshells. All right. And X-ray photons, as it turns out, are energetic enough to knock out core electrons. Right. So you can see that in the case of oxygen, this is knocking out the 1s electron. So it's completely ionizing that electron. And this is useful because, as it turns out, those core electrons are really specific to chemical environment. Okay, so just like in NMR, we kind of think of this as a chemical shift. Well, depending on the oxidation state or the chemical environment of our analyte, so in other words, is it an atom or is it a molecule? And if it is a molecule, is it a covalent molecule or is it an ionic molecule? So these very simple details are very sensitive to XPS. So the energies, the binding energies of these core electrons can be related to their chemical environment and molecular structure, which is really cool. And so XPS, as you can see here, so I'm kind of talking about these bullet points backwards. So it provides elemental composition analysis. So like I said, you can do elements or you can do molecules. And either way, what you end up getting is an elemental composition of your sample. All right. And also XPS is a surface sensitive technique. And so what I mean by that is if here is my analyte in question, okay, and let's just go back to that potassium metal example, right? Let's suppose this is K solid, all right? When this incident radiation comes in, specifically this X-ray, okay, photoelectrons are ejected. However, the only photoelectrons that make it to the detector are those originating from the surface. And when I mean the surface, I'm talking about a couple of molecular layers, right? So we know that some electrons will diffuse down into the surface and we never see those in the detector. So the electrons that make it out are only coming from a few, what I'll call mono layers. So just a few molecular layers. So this is also really cool because if you're interested in this surface chemistry, which is most useful in catalysis or in environmental atmospheric chemistry, like stuff that I'm interested in, that molecular interface is really important, right? It's where the gas phase experiences the solid phase. It's where those two phases will interact, or where a liquid phase experiences a solid phase. So being able to probe molecular details of an interface is really powerful. Okay, so here we have a picture of an XPS device, and these things are complex, expensive, and difficult to use. And that makes them really exciting. Okay, so here we have the detector. So this big old looking hat, we call that the Hemispherical Energy Analyzer. So that's the Hemispherical Energy Analyzer. And I'll show you a better schematic in the next slide. Okay, our sample rests right in here. And typically there's a little window viewport into this vacuum chamber. So this entire thing needs to get pumped down to about 10 to the minus 9 to 10 to the minus 11 torr. So we call that UHV. That is ultra high vacuum. 10 minus 10 torr, roughly. Okay, that is challenging, to say the least, to get a vacuum system to pump down to a pressure like that. Okay, so here is the X-ray gun, and they're actually called X-ray guns. So most typically, it's an aluminum anode that has a lot of energy pumped into it, and that evaporates off electrons. Okay, and so it's evaporating off electrons through this core shell interaction. So if we use, for example, aluminum, you typically hear this referred to as an aluminum K alpha radiation. And so K referring to the K shell, the N equals 1 shell, alpha referring to the principal line given off of aluminum. And so excitations from aluminum are made from its core energy levels, which gives off X-rays. Okay. So if you've seen this before, or if you've heard me say aluminum K alpha, that's an X-ray energy source, typically about 1,400 electron volts worth of energy. So that's a lot. That's a lot of energy. And as you saw from this previous slide, these binding energies of these elements are quite small. So those photoelectrons will come off with a huge amount of kinetic energy. All right. So let's see, what else can we talk about? And then finally, this long rod that you're seeing, that's called a manipulator. And so that's typically where you will place your sample. So you can see in this device, this little hatch would be opened up so you could place your sample on a little robot arm, and that robot arm will close up, seal everything, just like the International Space Station has a load lock and the main chamber, right? The main space station chamber where everybody lives. Well, that's exactly how these types of vacuum systems work. You'll have the load lock, okay, which can be exposed to atmosphere because this detector region will have a valve. It'll have some kind of way of shutting it off, all right? So this can stay under pressure. You place your sample in the load lock, and then now that you pump down the load lock, you open the sample chamber, the whole thing gets pumped down, and now these robot arms will actually move, right? It'll manipulate the sample right into the path of the beam. And that requires really high precision movement, right? To get that sample right in the beam path. So there is just a ton of technology and complication involving XPS. But that makes it pretty awesome, right? So let's get a better look at the hemispherical energy analyzer. Okay, so here you can see this is actually showing you several different photon sources. So the aluminum K alpha is the most common X-ray tube, aluminum K alpha. But if you were doing just regular photoelectron spectroscopy, you could absolutely do a UV lamp. You won't be probing the core electron levels, but you can still do photoelectron spectroscopy on the valence levels with a UV lamp. You could, of course, use a laser, or you could use a synchrotron. And so by synchrotron, that's a particle accelerator, such as LBNL. That stands for Lawrence Berkeley National Laboratory. So Lawrence Berkeley National Laboratory is one of the more famous synchrotrons in the United States. So it's basically a particle accelerator that can make any frequency of light that you want. So there is a lot of really cool XPS studies going on at the particle accelerator floor, where people pump particle accelerator radiation directly into their vacuum chamber to induce photoelectron spectroscopy. Okay, so here you can see photoelectrons are ejected off of the surface. And in this hemispherical energy analyzer, it kind of works much like a mass spectrometer, where it separates electrons based off of their kinetic energy. Now, in a mass spectrometer, everything has a constant velocity, but the mass changes. So that changes the trajectory that those mass ions will have. Well, in photoelectron spectroscopy, all of the electrons have the same mass, right? So what changes with these photoelectrons is their kinetic energy, and thus the speed that they come off the surface. Okay? And so faster photoelectrons will make it further onto the plate, and slower photoelectrons will make it, closer to the plate of the detector. Okay. And so typically these detectors are some type of photomultiplier tube, right? With some way of discriminating where each electron comes from. And that's how it can discriminate the electron's energy. So here is a typical XPS spectra. And so what we see here is there's one source of radiation. So this is typically, so if let's say this was aluminum K alpha, right? I noted that that's 14 eV. So we're only going to have one, monochromatic source of radiation coming off. The hemispherical energy analyzer will scan through all of the various kinetic energies. Okay? And as it's scanning through, it will find various peaks corresponding to those quantized electron orbital shells and subshells. Okay? So for example, if we look at platinum right here, you can see at very low binding energy, so this electron binding energy is calculated via the following. So we remember the photoelectric effect says kinetic energy of the electron equals h nu, the incident radiation, minus phi. Okay? Well, phi is really, as we said, the binding energy. This is what you want to determine. Okay? So the h nu, the incident radiation is constant. So by scanning different kinetic energies, right, and knowing that this energy is constant, we can measure the binding energy of various electrons in atoms. Okay. So for example, if we look at platinum, here we can see at a very low binding energy of, let's say like 90 electron volt, we find 4F. Okay. And as we keep scanning into higher binding energies, and keep in mind, right, these that 4F electron, for example, that's going to have the largest kinetic energy, consequently the smallest binding energy. And it makes sense that 4F has the smallest binding energy because it's the furthest away from the nucleus, right? And as we scan across the kinetic energies, we can see here now the appearance of 4D electrons, 4p electrons, right? And you can see those get to higher energies because we're getting deeper down into the core of the atom. All right?